In this section, we're going to start talking about some of the evidence for evolution and some of the testing that has been done to support natural selection. So, if Darwin's theory of evolution by natural selection is correct, then it should be able to make predictions that we can test. Now, keep in mind, Darwin, of course, did 20 years worth of experiments before he published this theory. We've had 150 years since then to test this theory. No evidence has pointed to a more likely driver than natural selection. Nothing has disproven natural selection. All right, so what should we be able to test? There should be evidence of species that lived in the past that are different from species alive today. We should be able to observe natural selection in nature. Now, we can't do this with long-lived species like humans. Over a human lifetime, not much happens. We can't, so we don't see this in our own experience. We can look at fossil evidence and trace human evolutionary history. But we can't see big changes in human evolution. We can, however, see big changes very quickly in bacteria, and I'm going to show you a video of that. And we should be able to see changes in species over time. Organisms that evolved from a common ancestor should have similar traits, and that makes sense. If the common ancestor developed a trait that was useful and advantageous, then that advantageous trait would be passed to the offspring. If it continues to be advantageous, it would continue to be passed to more offspring. So that makes sense, right? Okay, so here's a video, and I'm going to link to it on Blackboard. I'm not going to show it right now, but they basically set up a huge agar plate and put different levels of antibiotic on it and watch the bacteria evolve antibiotic resistance. This antibiotic resistance develops as a new mutation in certain individuals and then gets passed on to all of the offspring of those individuals. Okay, so we haven't talked a lot about the role of mutations in developing new traits, but of course that's where new traits come from. This has to be a mutation in the nuclear DNA in a germ cell so that it gets passed on to all of the offspring. If it's nuclear DNA like in your skin, that doesn't get passed on to your offspring. So if there's a mutation there, it's not going to affect anything past you. Does that make sense? All right. So evolution, evidence for evolution. We see fossils of organisms that aren't around anymore, like whoever this ginormous femur or thigh bone belonged to. We can see footprints of dinosaurs and other organisms that lived sometimes hundreds of millions of years ago. And the way these form is this animal walked across a muddy surface that then dried out. And if you think about, maybe there was when there's no rain, drought. And so it was able to dry really, really thoroughly. And then the next year there was a flood that brought a bunch of mud down very quickly and covered those footprints without washing them away because they were so dried. Now they're preserved, and then you just keep getting more mud on top that further preserves those. And then we have things called sedimentary fossils. For example, this is a tree where all of the organic tissue has actually been replaced by minerals, and that can happen at the bottom of a lake. Say this tree fell into a lake and there was very little oxygen at the bottom. As it gets covered with sediment, the minerals get pushed into the tissues and actually replace all of the organic structures, but leave the shape of the tree, and you get what we call a petrified forest. Darwin predicted that there should be transitional organisms between major groups. So here is a fish. You can see it's got little fins. Doesn't have a neck, oddly enough. Fish don't have necks. That's weird, right? And here is a land vertebrate that has legs that it can walk on and an actual neck that can turn. In Darwin's day, there weren't any transitional fossils, but he said there should be some. We have these fossils that show organisms that don't exist anymore. If small gradual change is the way that evolution works, then there should be small changes in between what we saw in those very old fossils and today. And we have found those through further research. One of the most important is this one right here, Tiktaalik rosier. And it was discovered by this man, by a team led by this man, Neil Shubin. He works at the University of Chicago. This is me with Neil Shubin with a cast of the Tiktaalik's head, and this is the actual fossil of Tiktaalik that they were able to find. And this is an artist's rendering of what Tiktaalik would look like. And you can see that it's got kind of flippers, but the bone structure inside those limbs is the same bone structure we see in vertebrate animals, land vertebrates. Not just vertebrates, land vertebrates. It's got a head that kind of looks like an alligator head. It's got the eyes and the nostrils on top. And it does have a neck, but it still has a tail that looks a lot like a fish tail. So this is an animal that probably would have lived in the shallows, on the edge of oceans or lakes. And they found it by looking at rocks that were between the ages of the rocks that delivered these two fossils. So if you look at an area that was an ocean or the edge of an ocean between these two time periods, that's how they found this. And they found it actually up in what is today Canada, northern Canada. So we can also see ancestors of humans, fossil ancestors of humans. One of the newest they found is Ardipithecus ramidus. They called her Artie because the individual they found was a female. And she lived about 4.4 million years ago. She was a direct descendant or direct ancestor of modern humans. And this organism, this group of individuals, shared a common ancestor with chimpanzees. And we can see the similarities in the skeleton. So this is the human skeleton, this is Artie, and this is a chimpanzee skeleton. And you can see, first of all, it's the same bones in the same organization, and that's true of all vertebrate animals, everything that has a vertebral column. But things that we see that are similar to the chimpanzee are the bowed forearm bones and the toe with an opposable big toe. So yes, I know you think you're very special for having opposable thumbs, but chimpanzees actually have opposable big toes, which is honestly kind of cooler. The pelvis on Ardipithecus is not as tall as the pelvis on a chimpanzee and oriented more like the smaller pelvis of humans. The skull has the opening for the spinal cord more at the bottom, whereas a chimpanzee skull has the opening for the spinal cord more at the back. So there are similarities between both because all of these organisms have a common ancestor. Okay, so these common traits are called homologies or synapomorphies. I know that's a big word. I prefer homology. Synapomorphies or homologies are similar characteristics because they were found in a common ancestor. So the bone structure, the organization of the bones, all of those things are homologies or synapomorphies shared between humans, Ardipithecus, and chimpanzees. Biological processes. The fact that you only had to learn one way of doing cellular respiration because organisms pretty much do cellular respiration the same way. That is a homology. Photosynthesis, homology. Digestion, homology. The presence of traits such as hair, feathers, teeth, and scales, these are homologies. So all mammals have hair because the common ancestor of all mammals had hair that was modified from the skin. Reptiles and birds, which are the same group, have skin that is scaly, that doesn't make hair. So that is, the scaly skin is a homology for reptiles. hairy skin is a homology for mammals. Homologies and different species are the result of divergent evolution, which is where one species diverges into multiple species. Now, the opposite of homologies are plisomorphies or analogous traits. Some people call them analogies, and I don't like that. And some people call them homoplasies, which I find very confusing, so I don't like that term. So these are traits that are not as a result of their presence in a common ancestor. So these are because the organisms live in similar environments or have a similar lifestyle. So birds and bats and insects all have wings, but the common ancestor did not have wings. So birds, bats, and insects all developed wings separately. Fun fact, most eyeballs, vision, evolved separately. Vertebrate animals developed vision separately from insects, developed vision separately from things like scallops and clams. Yeah, have eyes. Yeah, not very good ones, but they do. And all of those things developed eyes separately. So that's another plisomorphy or analogous trait. Sharks and dolphins, really easy to confuse because they kind of look the same. They're the same coloration, they're the same shape. But a shark is a fish and a dolphin is a mammal. But they both live in the ocean and swim really fast. So that is the result of convergent evolution. So divergent evolution is the creation of separate species with similar traits. Convergent evolution is similar traits, but not from a common ancestor. So they're remember, everything is at some point evolutionary related, but plisomorphies are not closely evolutionary related organisms. All right. So again, we see these homologies in the bone structure of all of these. Okay, so to look more closely at the forearm structure, the coloring here shows you the different bones with the humerus, radius, ulna, carpals, metacarpals, and phalanges. And all of these organisms, human, dog, bird, and whale, all have the same bones, slightly modified depending on their evolutionary history, their lifestyle, and their environment. These are evidence of a common ancestor. It's not proof. None of these things individually proves ancestry. But when you take all of this evidence together, it points to a common ancestor. And more importantly, it doesn't point toward anything else. One other thing that we see is vestigial structures, which are common structures that are reduced in some organisms. So all land vertebrate animals, vertebrate animals, have a tail that extends past the anus. This is different than like worms. Worms have their anuses at the very end of the organism, at the end of their tail. They don't actually have a tail. But in, say, dogs and humans, the tail is after the anus. The anus is actually here. In most vertebrate organisms, there is a tail that is outside of the body. The human tail is still inside the body. It's not visible outside of the body. Now, there is a mistake in your textbook about this, which says that vestigial structures have no function. And that is actually something that used to be accepted. We now know that all vestigial structures have some function. The function for the tail in humans is that it's attachment for muscles of the pelvic floor that help to keep your guts from falling out between your legs, because there's this big opening between your legs. Obviously, the pelvic floor here doesn't need to be as strong in an animal that walks on four legs. It has to be much stronger here. So there are some extra muscles, and those attach to this tail. So it's not correct to say that vestigial structures have no function. We may not truly understand its function, like the appendix. We think it has to do with the immune system, but we're not like totally sure. It does. So it's not no function, but it may be a reduced or different function. Okay, so that is some of the evidence for evolution. In the next, we're going to look at some more researchers who studied other things that also supported common ancestry.